So I'm not going to rederive the RLC circuit equation, but this is what it was. And I'll refer you to lecture 5, part 3. If you're interested in seeing the derivation again and reminding yourself how that works, that's where we did that. And we got this equation. We got this differential equation, where Q is the charge on the capacitor. So Q is our state of the system, Q of t. The derivative of Q is the current, I of t, which you could also think of that as a state of the system. Just take a derivative across the board here and track the current in time rather than the charge on the capacitor. Anyway, I'm mainly trying to point out the format of this differential equation. So the way we handled this before is we said, let's assume there's no inductor, right? We just cut out the inductor and put a wire here. And so we got rid of this term, and so it became a first-order linear differential equation. Then we were able to deal with it using our method of integrating factors. However, now we can introduce this, and this is a second-order, still linear, and I'll describe what that means, differential equation. And the techniques that we're going to learn for handling the damped spring mass system are the same techniques that apply to this. To start with, I'm going to assume that the right-hand side here is 0. So that means cut out this voltage source. So imagine just a resistor, capacitor, and inductor in a circuit. That sounds like, oh, I just took 3 components and didn't power the circuit, and I stuck them in a loop with no power. Nothing will happen. Yeah, nothing will happen if the capacitor starts out with no charge on its plates. But if you charge up the capacitor first, or maybe you introduce a power source on a switch, and then you just turn off the power source at some point, then once the power source is off and you just short it, you just put a wire in place of it, then you have a system where you have R, C, and L, and Q of t might not be 0. And it'll, as the capacitor discharges, you can watch what happens. And that'll be described by this differential equation where E is now 0. Okay, and why am I showing you this? Because look, it's another one of these differential equations where you have a constant times the second derivative of the unknown function, plus a constant times the first derivative of the unknown function, plus a constant times the unknown function equals 0. So this is another one of these second-order linear homogeneous differential equations with constant coefficients. Alright, that's the second time I say that mouthful of adjectives. Let's talk through what that actually means.